We're now going to shift to another topic related to integers. In particular, we're going to represent integers in different bases. We're first going to reflect on why we have 10 number digits. Then we're going to look at how place value works whenever we represent an integer in a decimal representation. And then we're going to describe how place value works in different number bases. So when we think about how our number digits work when we represent numbers, they are based on our hand digits. And when I talk about hand digits, I'm talking about our fingers. We have 10 fingers. That means we have numbers written in base 10, which means we really have 10 different symbols representing digits in our number system. So the counting rules that we use for place value, when we're literally counting from 1, 2, 3, 4, etc., is we start with 0. We count through all the digits, 0, 1, 2, 3, all the way up through 9. When we get to 10, something happens. And by 10, what I mean is we have 2 full hands of fingers. What we do first is we cycle back to 0. And then we increase the place value to the left of that by 1. And if there is no place value to the left, then we just stick a 1 there in front of that number. So we know how this works in base 10. If you start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Once you get to 9, we're out of digits. We cycle back to 0. And then we put a 1 to the left of that 0. And that's how we get 10. And then we keep on going 11 through 19. Once we get to 19, 9 cycles back to 0 again. We increase that 1 by 1 to increase the value of that digit. And we continue. We go 21 to 29. When we get to 30, we cycle that 9 to a 0. We increase that 2 to a 3 and get 30. And we keep on going until something interesting happens at 99. Now there, that first 9, that 9 on the right, cycles around to a 0. That increases the 1 on the left by 1. But when that happens, we cycle that one around to 0. And now we have no digits to the left, and we got to place a 1. And then we keep on going in that same way. Right? We know how to count. But the question is, how would this be different if we had only 4 fingers? And when I say 4 fingers, we have 2 fingers on each hand. So I call this lobster world because, it looks like a lobster. They have 2 little claws on each hand. I don't know. Trying to be creative. So we have the same rules here, except we have a different meaning of what it means to have 2 full hands of fingers. When we have 2 full hands of fingers, we have 4 fingers, not 10. So if we want to count as lobsters, we count 0, 1, 2, 3. Now, once we get past 3, we're going to have 2 full hands of fingers, which means that 3 is going to cycle around to a 0, and then we put a 1 to the left to give that 1, 0. Now, note that that 1, 0 that we're writing there is not the same as 10 as in the number of fingers that we have. That is in terms of 1, 0, the number of fingers that our lobsters have. And then we keep counting 1, 1, 1, 2, 1, 3. That 3 is now going to cycle around to 0 because we're back up to having 2 full hands of fingers. And then it's going to increase the 1 to the left by 1 to give us 2, 0. And we keep on going 2, 1, 2, 2, 2, 3. The 3 cycles around, increases that 2 to 3 to give us 3, 0. And then we go 3, 1, 3, 2, 3, 3. And now something interesting happens. That 3 on the right cycles around to 0, and then it increases the 1 to the left of it by 1, but then that 3 is going to cycle around to 0 as well, and then we have nothing to the left, and so we got to put a 1 there. And we keep on going 1, 0, 1, 1, 0, 2, 1, 0, 3. That cycles around to 1, 1, 0. That 3 cycles around to 0, and then the 0 increases to 1. And we keep on going, and the next time something interesting happens is when we get to 3, 3, 3. That 3 on the right cycles to 0. That increases the 1 to the left of that by 1, but then that one cycles to 0. But then that cycles the 1, increases the 3 to the left of that by 1, gives us another 0, and then we have to put a 1 to the left of that because there's nothing there. And we can go through this exact same process. We did this for 4 fingers, we did this for 10 fingers, but we can do this for any number of fingers that is at least 2. And we don't even have to have the same number of fingers on each hand. We can have 1 finger on one hand, 2 fingers on another hand, and do base 3 as well. So in general, if we let k be a number that is at least 2, and we want to talk about what happens when we count in base k, when we are writing a number of base k, we go through the exact same process as we did before. But I want to talk a little bit about the notation that we use when we actually write these numbers. So if we are writing a number in base k, we will generally write the k as a subscript at the end of a number. So in Lobster World, if we're writing in base 4, if we have the number 121 and we want to let other people know that we're writing in base 4, we will put 121 and then a subscript of 4 at the end, as shown there. If k is bigger than our number 10, that can be a little bit confusing, because if I put 16, is that 16 as in 16, the number I know, or is it 16 in another base? We're going to make that a little less ambiguous by just writing out the number. So if we are doing base 16, I'm going to write 125 in base 16, 125, and then literally take the subscript as the word 16. And also we have to worry if our base is bigger than 10, we're going to need more digits, right? Because as we can see, we need as many digits to write in base k as there are numbers k. So we need k digits to do that. So for instance, if we're writing in base 16, we need 16 digits. Well, we only have 10 digits, 0 through 9, so we're going to have to get some other symbols from somewhere else. Well, it's not too surprising. We're going to start with the alphabet. So for instance, if we're doing base 16, in addition to the digits 0 through 9, we're going to continue with A, B, C, D, E, and F. So A is going to be like our base 10 number 11, B is our base 10 number 12, etc., all the way to F, which is our base 10 number 15. And if we write a number just in base 10, our normal base, we'll just leave out the subscript. All right, so I want to talk a little bit about how we interpret place value in different bases. And in order to do that, I would like to start by interpreting place value in base 10, because that's something that we're familiar with. So if we have the number 48,253, I want to talk about what all those numbers within that, all those digits within that number mean. So for instance, that 3 at the very end means that there are 3 ones. And that 5 right next to it means there are 5 tens, right? So that actually represents the number 50. That 2 right next to that mean there are 2 100s. And the 8 next to that mean there are 8 1000s. And then finally that 4 at the end mean there are 4 10,000s. Right? And that enables us to understand what numbers we add together to actually get the number 48,253. So what we might ask is, what's the pattern? How do we figure out the pattern for the different place values that we have in base 10? Well, as you can see, each new place value that we have adds a 0 to the right, right? We go from 1 to 1 with 1 0, then 1 with 2 zeros, then 1 with 3 zeros, etc. And if you think about what that means, is every time we have a place value, we multiply by 10 to get them to the next place value. So we're really looking at each place value adding a factor of 10. And if we look at what that means in terms of how many factors of 10 we have, well, let's see what happens. So 3 and 5 look like they're going to be pretty much the same. 3 are 3 ones, 5 are 5 tens. Now for 2, there are going to be each of those things in 2 are going to represent a 10 to the 2, right? A 100, which is 10 to the 2. The 8 is going to mean 8 times 10 to the 3. 4 means 4 10 to the 4s. And in general, it looks like each place value represents a 10 to a power. Except for the first 3 and 5 might not look at it if you don't look at it too carefully. But if you look at it in a certain way, that 1 is the same as 10 to the 0, and that 5 is the same as 10 to the 1. So each of those place values represents a power of 10. In base k, it's going to be exactly the same, except being a power of 10. Well, really, power of 10 means a power of 1 0. And what 1 0 is in base k is literally the number k. So each place value is going to represent a power of k. So if we're looking at the number 2, 1, 3, 4, 5 in base 6, and we want to know what does that number look like in base 10, well, let's see. We can look at the place values. So that 5 means there are 5 ones. That's no different than base 10. So that just gives us plain old 5. Now for that 4, that is going to be 4 1 zeros. But remember, 4 1 zeros, that is 1 0 is equal to 6 in base 6. So that means they have 4 6s. So we get 4 times 6 is 24. That 3 is 3 times 100, but 100 is really 6 squared. So we get 3 6 squareds, which is 108. The next one over, that 1 is 1 6 to the third. That's 1 0 to the third. And that gives us 216. And finally, that 2 at the very end, that's 1 0 to the fourth. 2 times 1 0 to the fourth is 2 times 6 to the fourth, which is 2592. If we want to know what that number is in base 10, we just add them up, and we end up with 2,945 in base 10. So that gives you an idea of maybe how to do the activities. The name of the file is Introduction to Number Bases, and see if you can do those problems.